All right. So draw a reasonable Lewis structure, and by reasonable, I mean a correct one, for the following molecules and indicate both their electron and molecular geometry. And if y'all feel good about that, we'll maybe talk about determining if a compound is polar or non-polar. So based on yesterday's session, what is the first rule when it comes to drawing a Lewis structure? Right, so rule number one, that's a horrible one, is find total number of valence electrons, VE minus for short. So that's the first step. And how many valence electrons does silicon have? Silicon, not silicone. 4, exactly. It's in the same main group as carbon. Therefore, it's going to have 4 valence electrons as well. So 4 here. What about chlorine? 7. So 7, and we have 4 chlorines. So 7 times 4 is 28, plus the 4 is going to be 32. So we have a total of 32 because we have 4 times 7 plus 4. All right. So what's the next thing? Do y'all remember what the next rule was? Right. So find central atom, or determine. Let's. It's better to say determine the central atom. And the central atom is kind of clear whenever it's like SiCl4, but sometimes it's not as clear. But for in this case, which one is it? Silicon or silicone? Potato, silicon. Okay, silicon. And then we draw our terminal atoms like that. And the first thing we do is what? We now draw a single bond from the terminal atom to the central atom. So like that, like that, like that, and like that. So now we figure out how many valence electrons we've used up so far. So it's 32, and we've used up 2, 4, 6, 8. So we've used up 8. So 32 minus 8 gives us 24. And we know that we need to fill in the valence shell of chlorine, because right now chlorine only has 2 electrons because it's sharing these 2 with silicon. And silicon is good actually, because right now it has 8 valence electrons, right? It has 2, 4, 6, 8. So it's good. We don't need to worry about it just yet, but we need to definitely give a lot of lone pairs to each chlorine. So I say 1, 2, 3, 4, 5, 6, because it already has 2, so I need 6 more to complete its outer shell. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So in filling out those lone pairs, we ended up using 2, 6, 12, 18, 24 valence electrons. So with that, we need to subtract the final mass, so 24 electrons. Gives us 0 left over, which means we're all good. If we had an excess, where would those go? If we had, say we had left over 2 electrons, where would those go? It would go into the central atom as a lone pair, exactly. So, but what if we had a deficiency in the electron? So we ended up with a negative number. What would that mean? We need to form either a double bond or a triple bond. Exactly. Thanks, Sydney, and everyone in class that is eating their money today. So, but in this case, that's not what was needed. So we're all good. So the next thing you're going to be asked to do on a test is probably, or maybe it'll give you this structure and say, what is the electron geometry for the SiCl4? And you're going to have to figure out that out. So it's important. Let's see if I can go back one.
Really quickly, if it was 24 minus 22, and it was the 2, those 2 would go on the silicon, right?
Yeah, yeah, you would had 2 left over, assuming everything else has an octet already. Exactly. So worksheet 7. I wanna copy this thing over to the worksheet that we're doing right now. Paste. Okay, so every time we have 4 terminal atoms around our central atom, so in this case, we have 4 chlorine atoms around silicon. It's gonna fall in this category of electron geometry. So this is, all these are your electron geometries, okay? Everything to the right of them is a molecular geometry, but it's important to note that your molecular geometry can also be the same as the electron geometry. So in this case, I'll just tell you the answer since this is a brand new thing probably to a lot of y'all. We have 4 terminal atoms around our central atom. So it's like AX4, kind of like how it says right, AX4. That's what we're dealing with right here. AX4, basically, right? There's no lone pairs, so it falls under this category of tetrahedral, where its electron geometry is tetrahedral. So we would say tetrahedral, and these are all things you're gonna have to memorize all of these. It's really not bad once you categorize them, but at first glance, you're like, oh my gosh, I gotta memorize 5, 9, a bunch of over 10 different things, right? Well, it's not too bad once you find the pattern.
You
And-
also make some flashcards to help you out.
Yeah, exactly. So we said that its electron geometry is tetrahedral, and remember, electron geometry, you find that out by looking at the amount of electron dense regions around the central atom. So how many electron dense regions are around the central atom? We have 1 here, 1 here, 1 here, and 1 here. You really just count the bonding areas. And if you had, say you had a lone pair, how many electron regions would you have in this case? 1, 2, 3, 5, exactly. So you could have 5 electron regions if you had a lone pair, but because we have no lone pair and we just have 4 bonds around silicon, we have 4 electron regions. And that goes to a tetrahedral electron geometry. And because we have no lone pairs, our molecular geometry is also tetrahedral. So that would be the answer for both. The electron and molecular geometry.
And as a general thing, if you have no lone pairs on your central atom, if you all remember the trick I taught you yesterday about how to find the lone pairs on the central atom. So if you have 0 lone pairs, your electron and molecular geometry, more often than not, would be the exact same.
Yeah, so it's I think something that people get confused about is that your electron geometry will not always be, it's never going to be your molecular geometry, but your molecular geometry can be the same as your electron geometry. Because say you have a lone pair in this, let's look at, this one's good for, this one is the exact same as water. So water looks like this, HOH, lone pair. Central atom is oxygen. So the electron geometry for water would be, well, let's count how many electron regions are around oxygen. How many do y'all see? What? Can't hear you. Yeah, you're right. I just couldn't hear you. Sorry. So you have 4 electron regions, which falls under electron geometry of tetrahedral. But because you have 2 lone pairs, you have a bent shape. So that you get your molecular geometry is bent, while your electron geometry is tetrahedral for water. So that's why your electron geometry is never going to be your, I'm trying to say it in a way that makes sense, but your electron geometry will not be your molecular geometry, but your molecular geometry can be your electron geometry, just as we saw down here, if that makes sense.
What he's trying to say in less words is basically your molecular it's not, So your molecular and electron geometries aren't the same thing. You don't use the same term for both of them. It's only when there's no lone pairs on the central atom that you use the same term. So there's a different word if there's lone pairs on.
It's a little bit tricky to explain. Okay, it's like the whole thing of, what is it? A rectangle, a square can be a rectangle, but a rectangle cannot be a square. It's like that whole thing with the electron and molecular geometry. In this case, your molecular geometry is a square. And it can be a rectangle like it's electron geometry, but the electron geometry will not be
So
a
all
square.
all electron geometries are molecular geometries, but not all molecular geometries are electron geometries.
Exactly. So, sorry about that. Let's go ahead and do number B. It's really not bad. It's really not that bad. We're horrible at explaining that. And we apologize if we confused you, but we'll try to unconfuse you using the next problem. So what's the first thing we do? Find the total valence. So phosphorus has 5. Each bromine brings 7 to the table. So 7 times 5 is 35. So 35 there. So we have a total of 40 valence electrons. And then we now do what for step 2? Figure out the central atom. It's pretty obvious which one it is, right? Which one? Phosphorus. So Pe 1, 2, 3, 4, 5. Br. I'm kind of jumping a little bit ahead because I think y'all get the gist of where I'm going. But we put our terminal atoms around it and we drew a bond. So now we figure out how many electrons, valence electrons we've used up so far. So 40 valence electrons to start with. We used up 2 in this bond and 2 in each bond. So 2, 4, 6, 8, 10. So 10 minus 10 electrons. That gives us 30 electrons to work with. So next thing we would do is, let's just see, we know that phosphorus is phosphorus able to expand its octet, or is it only confined to 8 electrons max?
Think about it. It's a phosphorus atom. It's pretty large in size.
Expand, right? Because we know that elements that are in the 3rd period and below, they can have an expanded octet, and phosphorus is in 3rd period. Therefore, it can have an expanded octet because it has a d orbital. So now we just need to put in all of our valence lone pairs for the bromines, because right now they only have 2 electrons, they need to have 8. So we put 6 on each one. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We used up 6, 12, 18, 24, 30. So we used up 30 electrons. So that gives us 0 electrons left over. And again, if you had a surplus of electrons, you would put it on the central atom. We don't in this case. And if you had a deficient negative number of electrons, so you were deficient in electrons, you would end up incorporating a double bond somewhere into the structure. But in this case, we weren't deficient, so we don't have to worry about either of those 2 scenarios. Now that we have done that, and we realize that there's no lone pairs on the central atom, what does that tell us about their electron and molecular geometry? If there's no lone pairs, yeah, exactly, Cindy. If there's no lone pairs on the central atom, that must mean that the electron and molecular geometry are the same. So this is one of those cases where the molecular geometry is the electron geometry as well. So let's see, we have 5 electron regions, right, around phosphorus. We have 5. 1, 2, 3, 4, 5. Each bond is an electron region. So for now, it's okay that we're going to this table, but eventually you want to get to a time where you don't have to go to this table. And that'll be helpful to start memorizing this now. Your test is next Friday, it's the 28th.
2 Fridays from now.
Okay, so 2 weeks from now, you have plenty of time to memorize this. Don't wait, don't procrastinate, okay?
Honestly, I just stared at this table for like 5 minutes as I was walking to class and it helped.
Yeah,
The exam,
No, like before class. Or if you want to do it before the exam, you want to procrastinate like that.
I felt it was easiest to first learn each of these. And then you learn, okay, well, if I add a lone pair, what happens? Okay, well, if I add a lone pair, what happens? If I add 2 lone pairs, what happens? So I'm learning the general, when there's the general structure, when there's no lone pairs. And then I'm learning the structure immediately after you exchange one of the atoms for a lone pair. So you add 1 lone pair, what happens? You add 2 and you get the point now.
And pro tip for all the electron geometries, you'll eventually have to memorize all the bond names to go on with it.
Yeah,
Not for now.
not
but
for
like-
this worksheet, but you will for the test. So again, don't procrastinate if you can.
Is there a specific reason why those lone pairs get put where they're at? Like, you know what I mean?
Yeah, there actually is a specific reason. So it's all Vesper theory. So you want to put the lone pairs in the region that's going to give the most space between your bonds, because we know bonds contain electrons. Electrons repel each other because they're negatively charged. So you want to put the lone pair in a spot that's going to allow for the most space between your lone pairs and your electrons. So let's look at this one here. If you put, we call these axial, we call these equatorial atoms. So the ones that are like this, these are equatorial, and these 2 are axial. If you put them, if you put a lone pair on one of the equatorial atoms, it is 90 degrees to only 2 atoms, right? Because it would be 90 degrees to each of these atoms. But if you put the lone pair on, say, the axial position, it would be 90 degrees towards 3 different atoms. So it's all about Vesper and that stuff. You'll probably learn this in class, but it's very important in like classes like organic chemistry, when electrons are in certain areas and cause a certain molecule to have a certain geometry, which causes it to react a certain way. So I don't want to go further into that, but we will go ahead and continue on this question. So we have 5 regions, and that corresponds to which one? What was it? Yeah, trigonal bipyramidal, or if you have Dr. Armand, he'll say bipyramidal. So they're all the same thing, tomato, right? So trigonal bipyramidal.
You also might hear trigonal, like Trigon, King of Demons, but that's wrong.
Yeah, that one's wrong, like 100%. Okay, and then this is the same thing, so good thing we have an iPad, because we can just copy, paste. Alrighty, so I'm gonna do one more before I pass it on to Rish, because they have a couple more after that. Are there any questions so far? How are we doing, Daniel and Sydney and my non-Zoomers, my in-classers? Good stuff, Daniel.
if you have to add a double bond or like lone electrons to the central atom, does that change Your MG.
So you're saying if you had, let's see, let me give you an example. So if you had something like and like that. With four bonds to nitrogen, because nitrogen likes 4 bonds, and then one of them is a double bond. This is nitrous acid or nitric. So the electron geometry still does not change. It would be considered trigonal planar because it has 3 electron regions around it. So 1, 2, 3. That would fall into trigonal planar here. It's actually a very common thing you'll see in a lot of classes going forward. Trigonal planar carbon atoms. All right, KrF2. So krypton. Oh, krypton. Isn't that a noble gas? Yeah, it is. Doesn't matter. Krypton and xenon form bonds, even though they're noble gases. Let's go ahead and do our steps. Step 1 is what? Total number of valence. So 8 plus 7 plus 7. We do 7 twice because we have 2 fluorines. So that'll be 14 plus 8 is 22. So that'll give you 22 valence electrons to work with. All right, so which one's our central atom? Krypton, right? So Kr, and then we'll do F. Okay, so we used up in those bonds so far, we've used up 4 electrons, right? 2 in each bond, so 4. So minus 4 electrons, we get 18 left. And we know that krypton at least needs 8 electrons. And each fluorine needs 8 electrons as well. So we need to put 6 here, 6 here, and 4 more here because krypton has 4 right now. Whereas each of the fluorines only has 2 electrons right now. So each fluorine needs 6, and the krypton needs 4. So let's go add those in. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So that would be 2, 4, 6, 8, 10, 12, 14, 16. So we used up 16. So we have 2 electrons left. And whenever we have electrons left, what do we do with it? What? It goes on to the central atom. But when we have negative electrons, it goes into a double bond, right? Because negative electrons says we're deficient. That means we need to share even more bonds. We need to share even more electrons, so we need to form more bonds. If you just have excess or surplus of electrons, that just gets slapped onto the central atom because it's the most greedy one there. So those 2 electrons, let's do those, highlight that, those in blue. So we clearly have how many electron regions around krypton? Our central atom. 1, 2, 3, 4, 5. Yeah. So 5 electron regions. Let's see. Which corresponds to a electron geometry of what? Exactly. So trigonal bipyramidal. I hate spelling this one. Pyramidal. All right. And molecular geometry is, well, we added, this is where you would start doing your little, if you learned it the way I did, you would say, okay, we started off with trigonal pyramidal. We added 3 lone pairs to trigonal pyramidal or pyramidal. Well, what does it become? And because y'all don't know it yet, you should just look at this. If you add 1 lone pair to a trigonal bipyramidal structure, you get a seesaw structure. If you add 2, you get a T-shape. And if you add 3, you get linear. So whenever, and it's kind of convenient to remember that whenever you have 2 atoms, And who knows how many lone pairs, you're probably gonna have linear. The only time is that's an exception is when you have these bent and angular ones. But for the most part, if you have 3 or 4 lone pairs and 2 atoms, you're gonna have linear molecular geometry. So for the answer for molecular geometry would be linear. Any questions, or are we all good?
So if I didn't like write it vertically from the start, I would probably get this wrong.
Not necessarily, because I mean, this thing can rotate in space. It's not fixed like a standing person, like just like you're standing all day, but then you go to bed and you're laying down. You know, this thing is like a human. It can rotate, do everything. So you don't have to necessarily do it straight up and down. In fact, it could have been even diagonal. Just as long as you show, I think you would be wrong if you did this though. If you had done something like this. That would be wrong because you're implying wrong angles between the 2 fluorine atoms, even though we know that it's 180 degrees. So as long as they're on opposite sides, you would be good.
So would it be right if you did like the F krypton?
Yeah, so if you had them like horizontal, it would be right, as long as you're implying you're 180 degrees. So if it's F, you have 180 degrees here. Or if you had it like we did originally, like this. 180 degree difference here. Okay, yeah, so, and it doesn't matter if you did a slut. I thought we had a double bond because we were deficient 2 electrons, or let's see, we weren't deficient 2 electrons, because remember we started off. Let me fix this guy now. So we had that 1, 2, 3, 4, 5, 6. Okay, this is what we had after. I'll go through the steps. So we started off with 22, and then we used 4 up in the bond. So we did 22 minus 4 to get 18. And we realized that before we got to this step here, we needed to put at least 2 more electrons on krypton to give it 8, right? Because it had 4 to begin with. And we needed to put at least 2 more lone pairs to give it a total of 8. So we needed to put 4 here. We needed to put 6 on each fluorine because each fluorine only had 2 to begin with, and we want them to have 8. So we need to put 6 on each fluorine. So 6, 12, 18, wait, 6, what am I gonna do? 6, 12, 14, and 16. That means we used up 16 electrons in that step. In going, I think that's rule number 3 of rules, Rich's stuff or whatever. So we used up 16 electrons. So we subtract the 16 electrons, we get that we have 2 extra. Because we had 18, we used up 16 in the lone pairs, and we had a surplus of 2 electrons. We didn't have -2. If we had -2, lone pairs would need to come in, but we didn't have -2. So what we do with those is that goes onto the central atom. Only when you have a surplus. Does that make sense, Sydney? I think she's tired. Okay, I think that's what confused me. I thought it would. Oh, yeah, sorry, I might have accidentally put a negative sign. The first time around, but we had 2 extra, not 2 deficient electrons. So now you're probably wondering, Dylan, why do I have to learn this stuff? Why is this important to me? I'm a biology major. Why is this? I don't understand. Well, do y'all know these structures? from biology class, maybe?
No.
Have you all ever heard of ATP? Well, that is ATP. And these structures, they don't show the carbon atoms, but every little point connection here is a carbon atom. So you have a carbon atom here, here, here. It's because it's really tedious to draw each carbon and hydrogen atom, because right here we would have carbon and a hydrogen, but we don't want to draw that. So instead we just put a point there. But you're probably wondering, why is he showing me organic chemistry right now? And this is just biology, actually. It's not organic chemistry. The organic chemistry is the next step. And so this is all happening in an enzyme called hexokinase, which is in the first step of glycolysis, which maybe sounds familiar to you. And what happens is basically some base, we know bases like to deprotonate things. They like acid-base reactions are the transfer of protons. So a base takes away this proton and these electrons attack phosphorus. And look what you get in the next step as an intermediate. You get a new trigonal bipyramidal phosphorus. And I was like, whoa, I was looking at this earlier. I was like, whoa, Gen Chem 1, let me show you all this. But look at this. This phosphorus is exhibiting some trigonal bipyramidal electron and molecular geometry. And I didn't show the next step, but it just collapses and you form glucose 6-phosphate and ADP, adenosine diphosphate. So if this is not cool enough to make you all become biochemistry or chemistry majors, I don't know what is. But it was pretty interesting to me when I saw this earlier. I was like, I gotta show them this. And that's crazy. Tried so hard. It took me a whole 30 minutes to make this. You know what? Here, Rich, I'm done for the day. I'm just kidding.
All right, let's do some bio major chemistry. XeF5 plus. What's our rules again? What's our first rule? Yeah, identify the number of total valence electrons. So xenon has 8, and then fluorine has 7. So 7 times 5 is 35, plus 8 is 43. That's our total, right? Sure. Why? Yeah, there's a plus there. So what do? We add an electron, right? Because the plus means +1. What does it mean? -1. So 43 minus 1, there's 42 valence electrons. Now, let's not use the trick for this one. Let's do it the long way. So xenon, F, 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 another F, another F. So connect all these with bonds. That's 10 electrons used up because I made 5 bonds. So 42 minus 10 is 32. And then we have to make all these fluorines happy. So we're going to add 3 lone pairs to give them a total of 8 electrons. 2, 3, 4, 5, 6. All right. And then that was 30 electrons we used up to make all those fluorines happy. So we have a total of 2 electrons left. Now, where do these 2 electrons go? Central atom, so on the xenon. So let's place them here. Then -2, this is 0. And then we're done here, right?
What else do we have to do, Sydney?
There's an extra rule for when stuff has charges. I don't think I went over it yesterday. Yeah, you have the plus sign in brackets. So what I do, just put the structure in brackets and then put a plus right here, like that. Granted, the brackets are better drawn than this, but yeah. Basically, you do 2 sets of square brackets like that, and then you put a positive sign. So what is our electron geometry? If we scroll up, there's how many electron regions do we have? Yeah, we got 1, 2, 3, 4, 5, plus the lone pair 6. So 6 electron regions, which means our electron geometry, if we scroll up a fair bit, is what? Octahedral, yeah, that's exactly how you say that.
Confident with your chest. Were you just unsure on how to pronounce it or, okay, yeah. It's, these are weird words.
Octahedral. And then if you look at your molecular geometry, let me see if I can test myself here. There's 5 things, 1 lone pair, so this is square parameter. And if we go up, 5 bonds plus 1 lone pair. So if you add a lone pair to your octahedral, this is indeed square parameter. Then if you add 2, it's square planar, then T-shape, and yeah. Honestly, just stare at this chart for a good few minutes. And then if you do a bunch of practice problems, and then you're like, okay, this is trigonal bipyramidal, so this is what a trigonal bipyramidal structure would look like, that'll also help you out as well. At the end of the day, you're just substituting atoms for more atoms. Would it help to actually see these in 3D? Like molecules in 3D?
Pretty sure you're not a good drawer.
Oh, no, I don't have to draw. I can use computer software to do it for me.
Oh, that's cool.
Yeah, that's what I do in my lab all the time. Take 3D structures and basically looking at those all day.
You must feel one with the atoms.
I'm the molecule.
It sounded like, I forgot the name.
Certain. All right, anyway. XeO3, sorry, or wait, any questions on the last one? How I got to what I got? Right. There are no further questions. We shall be taking our leave to the next question. XeO3. So what's our first step again? So that'll be 8. Then each oxygen carries 6. 6 times 3 is 18 plus 8. That's 26 electrons. So now, what's our next step? Yeah, what's our central atom? Yeah, xenon, and then slap 3 oxygens around it. Here, here, and here. So boom, boom. So -6. 20 valence electrons. Now what do we do? And the rest where then?
Central atom
The
first.
central atom?
All 20 electrons on the central atom?
What?
Yeah, and the surrounding atoms. You got to make sure all the oxygens are happy first before you go on to the central atom. So I'm add 6 to make these oxygens happy. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So minus 18. It's 2 electrons left over. We're going to slap those on the xenon. So 2 minus 2, that's 0. All right. We liking this structure? Is it good? Is it bad? Is it somewhere in between?
I don't know.
Well, this is actually the structure of XeO3 for now. Once we learn about formal charges, we can change it up. But this is a valid Lewis structure for XeO3. Now, looking at this, what is our electron geometry? How many electron regions do we have? Yeah, there's this one, this one, this one, and the lone pair. So electron geometry is tetrahedral. Now, what's our molecular geometry? If we scroll up, we're in our tetrahedral electron geometry, and we notice that there's 3 bonds and 1 lone pair. So what do we call that? Remember, it's not the king of demons. It's not trigon. It's trigonal parameter.
Try John. That's funny.
Y'all know what I'm talking about? Have y'all seen Teen Titans before?
Okay.
Yeah, like Trigon, Raven's father, yeah. Trigon parameter. Trigon. Yeah, I mean, if you think about it, yeah, it's kind of weird, right? Because triangle is pronounced triangle, not triangle. Though technically it is triangle because there's three angles, but that's why they call it a triangle. But anyway, you get the point. The molecular geometry is trigonal parameter. Trigonal parameter. All right. Any questions on that? Room people and Zoom people. Try to think of a word that rhymes with people. Hmm?
All good,
All good.
Danielle says.
All right. Now CO3 2 minus. What's our first step again? Low valence electrons. Carbon has 4, oxygen has 6. 6 times 3 is 18, plus 4 is 22. But this is 2 minus, so we add 2 electrons. 22 plus 2 is 24. Shout out Kobe Bryant. 24 valence electrons. So now what's our central atom? Yeah, because 9 times out of 10, if you have a carbon-based compound, it's central atom. And it has the least electronegativity out of the 3. So oxygen, oxygen, oxygen. Now we're going to connect each of these with a bond. Boom. So 24 minus 6, that's 18. And then we gotta put all our lone pairs on the central atom, sorry, the surrounding atoms, make sure they're all full. So 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, until these have 8. So that's 18 here. So we have 0. But carbon needs some more electrons to be happy. So we're gonna put 2 right here on the carbon. And that means that we have -2 electrons. What happens if we have -2 electrons? Yeah, which oxygen do you want to place the double bond between? Does it matter? I'm asking you.
I don't know.
What do you think? Well, what's your gut instinct? No.
No.
No, or yeah? All right, Daniel's going with the bottom. Guess I know what he is. Okay, anyway.
You're recording for YouTube and demonetized.
Anyway,
Nothing was said. That was weird.
it wouldn't be the first time I said something. All right, anyway, does it matter or does it not matter? It does. What do you say?
I guess it does.
It doesn't. The correct answer is that it doesn't. Because let's place a double bond right here. So what happens is these Lewis structures there are 2 identical structures that can be drawn, right? We have this one and then one where it's like this, or I'm not going to draw the whole thing for simplicity's sake, but there's one, or let me erase my math.
You can space them out. I purposely put a lot of space on this worksheet so you don't have to.
All right, so there's one like this, and final one like this. These are what are called resonance structures. Resonance structures are basically where the Lewis structures are the same, they're between the same atoms, but there's a different arrangement of the electrons. The double bond, or in this case, the double bond's on the right, the double bond's on the bottom, or the double bond's on the left. And frankly, it doesn't matter which one. The reason being is that which structure is right, do you think? If you look at a carbonate molecule, where would the double bond be? On the right, on the bottom, or on the left? Or your fourth option is all 3. Yeah, it is actually all the above, because we can draw what is known as a resonance hybrid. So. Here. This. The double bond actually rotates between all of them. That's what is, this is what is called a resonance structure. And of course. Yeah, that's your resonance hybrid. You draw the lone pairs as well, but who cares about those? So, yeah. Basically. This is why, so if you look at a carbonate molecule, it's actually a combination of all three of these resonance structures. Sometimes a double bond could be on the right, sometimes it could be on the bottom, sometimes it's on the left. Frankly, the true structure, it's a combination of the three. So this is what we call a resonance structure. Let me write that out. Resonance. The thing over here is called a resonance hybrid. The things on the bottom down here are resonance structures. Resonance structures. The double-headed arrow I drew is like, that is like an indication of resonance structures. So like if you have two resonance structures, you draw a double-headed arrow between them. All right. And another nifty trick is if you have an oxygen with a charge, like a polyatomic ion with a charge, the charge tells you the number of single bonded oxygens. Single bonded oxygens. So in this case, as you can see, there are two single bonded oxygens. So this 2 minus right here tells you that there's going to be two single bonded oxygens. So if you took nothing away from what I said, basically you draw out one structure for a resonance structure. And then you sort of move the double bond between all three of the oxygen atoms, because you equally could have put it on the right, bottom, or left. And frankly, any of them are right. So you have that, and then these are called resonance structures where the bond fluctuates between the three, and the charge of the ion tells you the number of single bond oxygens. Does that make sense to everyone? Y'all may or may not have to draw out the resonance structures of carbonate on one of your take-home assignments. But if they ask you to explain it, it's the exact same way I did up here. And if you draw this thing, Dylan and I will think you're extra smart. Probably
I
not,
got a
because,
question.
yeah,
So on the previous one, you wrote the oxygen on top, but this one you wrote on the bottom. Does that matter?
wait, for which one? Oh, this one? That it doesn't matter too much, I would say, but like as Dylan said before, like make sure you get your angles correct. So, or not correct, but like don't draw something that's like, say for example, CO2, don't draw it like this, because it's that implies that it's not a 180-degree angle, which it is. But for this one, I'd say like for now you can draw it out like wherever you want, but yeah, make sure that your angles are at least somewhat correct. Like if it's a 90-degree angle, make it somewhat look like a 90-degree angle. That makes sense?
Yeah.
But yeah, let's go to our electron geometries and stuff. So what is the electron geometry of our carbonate? So there's 1, 2, 3 electron regions. And if there's 3 electron regions, what geometry is that?
The planar,
Which one? There's a lot of players.
the second one. Trigonal, there you go.
Ah, dang it, I can't do that thing now. Trigonal, okay, trigonal plane. That is the geometry of our electron geometry of our carbonate. What about our molecular geometry?
Same.
It is the same, because there are no lone pairs on our carbon. Trigonal. If y'all need to actually see these in 3D, say the word, I'm not gonna make it happen.
So Rich, you're saying that the double bond doesn't affect the molecular geometry?
double bond does not indeed affect the molecular geometry.
Good.
As there are, we base it off of electron regions, not necessarily what those regions are. So like a lone pair would have the same effect as a single bond, which would have the same effect as a double bond, which would have the same effect as a triple bond. All we care about is, are there electrons there? If so, cool, then we run with it.
Okay. Interesting. But only lone pairs on the central atom affect the molecular geometry.
Yeah, only lone pairs on the central atom will affect your molecular geometry. Because once we learn about polar and non-polar, you'll see why that's the case. The addition of some lone pairs on the central atom will make certain molecules polar.
There gonna be a question where we have to, or they give us the structure and we have to say what it is.
So like, if I gave you this structure, and then you'd have to say what it is. I don't know if it'll be as cut and dry as that, like, they might ask you to draw out the resonance or the Lewis structure for a certain compound. But I don't know if you have to go from compound or Lewis structure to compound. But I would still practice that anyway.
I think it was multiple choice too, like, it's like, what is the correct Lewis structure for this formula? And then it gives you multiple choice options where you select it, so you're not gonna be drawing anything, because it's all a multiple choice exam. But you will need to know which one is correct by, I mean, you probably end up just drawing it yourself, so you can see which one is the correct answer choice. But you're not gonna necessarily be punching in, I mean, there's no way you can punch that into your eye clicker, you know?
Yeah. Maybe some mess, yeah, there'd be some scuffed away if you did it. But yeah. Are there any questions on that, on resonance structures? Or or what the charge tells you of an ion? This is only for oxo anion, by the way, so anions with oxygen atoms. Or just polyatomic ions in general with oxygen atoms. It's the only place where you can apply this.
I have a couple multiple choice questions below
Yeah.
before we end.
Here's some multiple choice questions. The electron geometry of the central atom in PCl3 is what?
So this is the type of question you would probably like bar for bar see on a test, maybe not the same formula, but it's gonna ask you, it's gonna indirectly require you to draw out the Lewis structure for that and then determine the electron geometry.
Yeah, so the steps for this question is like step 1, you're gonna draw out your Lewis structure. Draw Lewis structure, and step 2. STRUCTURE. Step 2, figure out. That bad?
Yeah.
Alright, draw Lewis structure.
It's like you try to mix a combination of cursive and regular writing, so it's like a resonance hybrid. It's like between the two.
Find electron geometry. Better? This is why I stick to numbers. Nobody clowns you for numbers. All right, PCl3. We find our total valence electrons. So that's 7 for each chlorine and 5 for the phosphorus. So 21 plus 5, that's 26. What do we do from here? What's our central atom? It is indeed the P. PCl, Cl, Cl. And now what do we do? Boom, boom, boom. Now that's -6, that's 20 electrons. Now, what do we do from here? Yeah, so. I'm gonna fill them out, so that's 8, 1, 2, 3, 4, 5, 6, that was 18 we used up. That's 2 left over. So where do these 2 go? On the phosphorus. So -2, 0. So that being said, there's 5 electron regions. What is our electron geometry?
Sydney says something.
All right, trigonal biparameter.
Wait, am I blind? Where's their 5?
Oh, yeah.
Look at four.
One, oh wait, there is four. I'm stupid. Yeah, I'm stupid. Okay, four electron regions. Not bad. Yeah, there is, because there's 1, 2, 3, 4 right here.
It was a trick question, guys.
Yeah,
He was just making sure y'all are paying attention.
exactly.
Oh, Daniel says you're lying.
Just kidding. All right, 4 electron regions. So now that being said, what is our electron geometry? If there's 4 electron regions.
Picture still.
Think about which of these words mean 4. Tetrahedron, option C. And if we'll confirm it with a picture. Yeah, four things around it. 4 things on this tetrahedron.
And
4 around it.
Cindy, you said if it was 5 things around it, so like four atoms in a lone pair, it would in fact be the trigonal bipyramidal electron geometry. But if it was 4 atoms and a lone pair, the molecular geometry would be C. So in that case, you have electron and molecular geometry that differ. So you gotta be careful and see, you actually have to see what the question is asking you. Is it asking about electron or molecular geometry? Sweet.
And second one for our purposes takes way too long. And we cannot do that in a minute. So, yeah.
We'll call it a day here and we'll finish up on, oh,
Thursday now.
yeah, Thursday, because we have now another session for a different class on Monday, unfortunately.
Did you guys actually get people?
We got like 30 people.
Yeah, but it was an example.
Yeah, but I have a feeling we'll still get just as many people. Well, okay, maybe a little bit less, but like, maybe like 15. Yeah, you're welcome, Sydney. Have a good one. Yeah. You too, Danielle. This guy, Rich, said he was a numbers guy and proceeded to mess up the number. You don't get clowned on for numbers. Daniel says, clown proceeded on you for numbers. What do you got going on this week?